All right, just a chance there to switch to a new page in my notebook and get ready to start here. Once again, this is Neil, W2NDG, and we are starting the OMARC Sunday Night Science and Technology Net. We gather here every Sunday night at 8 p.m. to discuss subjects of science and technology, not always ham radio related, but sometimes they are. And I am usually accompanied by my cohort and co-host, Jim, K2BHM. Jim, are you around tonight?
I'm here, W2NDG, K2BHM.
Well, good evening, Jim. And I apologize for not emailing you in advance, but pretty simple topic tonight. And we're going to talk about the cold. And what cold actually is. And we can get into, I think, some practical uses for it. So we are here on the repeater of the Overlook Mountain Amateur Radio Club on 146.805 megahertz with a negative shift of 600 kilohertz and a PL tone of 103.5. If you'd like to join in with us tonight, you can also find us streaming live on YouTube. Simply search for W2NDG Science and Technology in Google or YouTube, and you'll find my channel there, and we are streaming live on YouTube. You can join the conversation through the chat there or check in on the repeater, either or. Special comment for the YouTube people tonight. I don't know if there's anybody watching yet, but even on the replay, you're probably wondering what the swatches of color are on the walls here. Is KD2CHE is trying out some new color schemes for the office here, and I'm supposed to pick one of these. The yellow is probably out, and there's a couple other colors in front of me as well, but I'm leaning towards that darker color. Anyway, cold. And one of the things that I wanted to get into tonight is what it really is. You know, it definitely was at the forefront of our discussions and tops in our minds after last night. It got to -4 Fahrenheit here overnight. And looking at, some of the maps and charts I mentioned this morning that, in Messina, New York, it was 16 below zero overnight. Somewhere near Saranac Lake, it was 21 below. That's cold. But is cold really a quantifiable thing? And the answer is no. There isn't a force. There isn't a measurable energy called cold. Cold is the absence of heat and is measured as such. So the perfect example of this is an air conditioner. And from our observations, and we're not incorrect, when we observe what an air conditioner is doing, it's blowing cold air into the room. We can feel it. You can put your hand in front of it. You feel the cold air. But what is actually happening scientifically is that the air conditioner is removing heat from the room. It's the reverse of what we think. And those BTU ratings that you see when you buy an air conditioner are actually for the amount of heat that the air conditioner can move out of a space. And this is what it is. When you touch something that's cold, it's not that the item is cold, it's that it's drawing heat from your finger or hand. It's an object that has less heat than your hand, and different objects draw energy at different rates of speed. Some metals are extremely good conductors of heat and will feel colder than others. And a lot of strange phenomenon happens when we get near the limits of a lot of the heat transfer mechanics. Two that I can bring up are one, there are situations, provable, where hot water freezes faster than cold water. And that is actually a principle that has to do with the excitement of the molecules in water. And that when they're in a heated state, they're already excited. And there is a point when they start to freeze where they become excited. So there's kind of like a shortcut there. I know I'm oversimplifying that, but that's what happens sometimes when hot water can actually freeze faster than cold water. And another interesting phenomenon that you'll see sometimes is something that they call the slingshot effect. Certain metals and substances can, if they cool too fast, can actually dissipate so much heat so rapidly that they will travel beyond the actual temperature of the air. So what happens every now and then, when the temperature drops really, really fast, you will find frost on your car, either on the metal or on the windshield. And that's a result of the temperature dropping so fast that the temperature of that surface dipped below the air temperature, cold enough for it able to freeze moisture that was in the air. So that's another weird one. There's plenty of others. There's sublimation, which is what gives us freeze drying, and all sorts of crazy things. But so the next time you see ice, you can say to yourself, well, that's not water that got too cold. That's water's natural state in the absence of heat. It'd be kind of inconvenient if it was all solid. Anyway, that's my introduction to tonight's topic. And let me hand it over to Jim for any expansion on that he might want to offer.
Thanks, Neil. Interesting topic tonight, K2BHM. Lots of information there. Lots of details, lots of things. I don't know how deep you want to get into
it. Probably not ridiculously deep. I don't want to go super late tonight again because I'm still watching over an under the weather XYL. But what I was going to offer out to everybody is, if you know something along the lines of this subject, a story, an example, something you've experienced, a little tale you want to tell, that's fine. If you want to give us a practical use, and even the obvious ones, of the removal of heat, what practical uses do we use extreme cold for? One of these relates directly back to our food preservation topic. It's a huge step forward, refrigeration. But anything like that, any of your experiences with it, strange things that happened when you observed something freeze in an odd way, anything like that. Places you've been where things are just so different because it's so much colder. Anything like that. So very open tonight, the topic of cold, whatever you want to talk about. So anyway, so Jim, any direction really. And I know, yes, we could go on for hours about thermodynamics and all sorts of things. The heat plays an important part in physics and all sorts of things that make the universe tick. And the absence of heat can be examples of when the universe stops ticking in some ways. But heat is a byproduct of almost anything that happens. You can relate it back to that. So the absence of heat, the removal of heat, It's a pretty broad topic. So, how's that, Jim?
Yeah. Well, basically, everything has heat. It's just a case of how much of it, and it's all relative. And we can go on from there. Why don't we see who's out there?
Yes. So, let's take check-ins. And to check into the Sunday night Science and Technology Net, give me your call sign, your name, and your location, and I'll make a list. Come now.
I'll go N3 UIQ. Peltier K2LD. KB2GGF.
All right. After Jim and I have 3 check-ins so far. Paul, N3 EYQ in Blooming somewhere. Bob, K2LD up in Tannersville. And Matt, KB2GGF in Kerhonkson. Matt, your signal's really weak tonight. I think your antenna froze. All right, Matt, if that was you again, it was even worse than the first time. So we'll let Matt work on his setup there. And is there anybody else who would like to check in before we start talking?
Control. 82 TVS Lou Westmore.
All right. Welcome, Lou. And we'll take another chance for check-ins, so don't worry if you didn't get a chance now. When we get through the list, we'll do it again. All right. So, Jim, I'm going to start off with you. I'm sure you have, you probably have trouble deciding what to talk about here. But give us a good science example or a great story or anything like that.
Yeah, okay, thanks, K2BHM. I thought it'd be a good start to basically figure out what temperature is. Everything in the universe has a temperature. It's just a question of how much is it. So what is temperature? Well, the molecules in a rock are solid. They don't go anywhere. And the molecules in water flow very nicely. And then gas, they defy gravity and just bounce all over the place. But no, actually, all molecules are moving. It's a question of how fast. So temperature technically is the measure of the average kinetic energy of the molecules of the sample you're looking at. So a rock, they're going very slow. A gas, they're going very fast. And heat is basically the measure of how fast molecules are moving. And also at certain particular points, we have what's called a phase change. Solid, liquid, and gas. Water is a good example of that because it's very easy to see all three. We'll see it later on tonight and tomorrow. So let me drop a second. So basically, molecules that are traveling very slowly, low temperature, and they're in the solid condition, ice. And as the energy level increases, there's a certain phase transformation that happens between ice and water. And then another phase transformation happens between water and gas, which we would call steam. So now how do we measure how much heat is there? There are ways to do it with electricity, electric charges, and stuff like that. Well, they figured out that the amount of heat to take 1 pound of water and raise it 1 degree Fahrenheit is 1 BTU. And likewise in a metric, 1 gram of water, 1 degree centigrade is 1 calorie. Well, where do we get Fahrenheit and centigrade from? Let me drop again. Well, Fahrenheit is easy. Some guy over around the Mediterranean figured that how cold does it ever get? And he kept records and made that 0. And how hot does it ever get? And again, the records, he came up with the number 100. So the Fahrenheit scale goes from 0 to 100 as the coldest and the hottest it ever was in this particular little village around the Mediterranean. And then as things expanded, we found out, well, yeah, the temperatures go below that and above that. So centigrade came about and used 0 as the freezing point of water and 100 is the boiling point of water. And that became the centigrade scale for the metric system. So let's back up again a minute. Let me drop. So now what about these phase thingy changes? As water is the state of ice warms up, when it gets to 0 degrees centigrade, it takes 80 calories now to convert 1 gram of water or 1 milliliter of water to ice or ice to water. And then when we get to the other end of the scale, it takes 540 calories to go from water to steam or steam to water. And a little hiccup in the curve there. And so that's where that came from. And basically, like aforementioned, everything in the universe has a temperature, a certain amount of energy in it. Starts at absolute 0 and goes up to the temperature of the face of the sun. So what normally happens is, let me drop. Normal flow of things is for energy level to go from the higher excited energy or a higher temperature to the lower. And there are all kinds of equations and parameters to do that. There's specific heat, how many calories or BTUs is going to change the temperature of your medium, how many degrees. Water is the standard of 1. And it goes on from there. All different places have different specific heats. And there's a different conduction, steel versus aluminum versus copper, whatever. Just like wires have different resistances for electricity, they have different resistances for thermal conductivity. So there's a lot of parallel tracks there to go down, and lots of room for discussion here. But that's pretty much the basics. So let me throw it back to Neil and see where you want to go from there. K2BHM.
No, Jim, that's fine. Good, and a good background for purposes of discussion. When we talk about temperature, it's good to understand what we're actually talking about. And thank you. That was great. And there has to be some amount of heat for things to function. And when there is 0 heat, which is a figure, and you can correct me if I'm wrong, Jim, before we move on, absolute 0 is the absence of heat completely. Things cease to function at that temperature, correct?
Yep. If you were to have like a gas, like helium, as you bring the temperature down and down and down, the activity gets less and less and less. And helium actually converts to a liquid at, centigrade zero would be freezing, and absolute zero is minus 273.15 degrees. So they generated a scale called Kelvin, where absolute zero is zero, and water freezes at 273.15 degrees. Well, somewhere around 4 degrees Kelvin, helium turns into a liquid. If you were to get it down to absolute zero, it would turn into a solid and then cease to exist. But in any event, interesting things happen down at that low of a temperature. Like certain conductors, all the resistance disappears, and you have a superconductor. And with a superconductor, you can make a supermagnet, and you can make yourself an MRI system and run your own imaging center. Back to you, Neil, K2BHM.
One of my favorite demonstrations that hobbyists will build, if you're talking about extreme cold temperatures and superconducting, is the Levitation Experiment. I assume you're familiar with that.
Not sure which one you're talking about, but there's another interesting one that's probably somewhat similar, but in a different plane. If you take a sheet of aluminum, like a speed limit sign or something like that, and put it at the bore of an MRI, where a person would go into the hole and stand it straight up and let go, it will start to fall down. But it does so very slowly, because a conductor passing through a magnetic field generates an electric current. And the electric current going through the sign generates a magnetic field, but it's in opposition to the one that caused it. So the plate looks like it's falling in slow motion.
Yeah, I'd love to see a demo of that. I'm sure I can somewhere. It's the joy of the internet. I'm looking, and what I was talking about is super diamagnetism. There were a couple of projects that duplicate the Meissner effect, where you can levitate an object over a supercooled superconducting magnet, and it will appear to just freeze in space. It doesn't have like the as much of the springy qualities of regular magnetic levitation, which is where you can balance things magnetically, but definitely interesting, and a cool experiment that it's one of those ones that you can actually do yourself. Anyway, cool stuff, but we can go around to the people who have checked in so far, and if you have anything you want to add to this, something you've observed, or an interesting tale of something weird that happened because of the cold, or something productive that you did with it, all sorts of things. You can basically go in any direction with this, but we'll take your stories or your comments, starting with Paul, N3EYQ. Please come in.
Oh, I always thought the Fahrenheit scale had something to do with Daniel Fahrenheit, physicist who came up with the whole thing. And somehow or another, I thought 0 was the freezing point of brine, and 100 was supposed to be, I believe, the average body temperature at one time. But that's what I thought. Oh well. And I was poking around on Wikipedia, and it kind of throws something about the average body temperature. It's about 98.6. So somebody was wrong somewhere along the way. And of course, calories and all that stuff. I remember all that from high school physics. That was interesting. 0 degrees was the freezing point of water at sea level. Regular, the normal pressure at sea level. Standard pressure at sea level, and of course, 100 was the boiling point at sea level. Oh well, yeah, kind of interesting to say the least. Kind of makes me remember about all the high school physics stuff I took. N3EYQ.
No, the body temperature comment. I mean, Close enough without, accurate ways to measure things. I mean, there's a reason why the foot is called a foot. And it's not just coincidence that it's the same name as what we walk on. Um, all sorts of things like that grew out of the measurement of something that was common but not standardized, if that makes sense. So it definitely makes sense that that's where some of that could come from. And you mentioned temperature at sea level. It's something we didn't bring up, but pressure has an effect on all of these numbers. And when you graph the state of something along pressure and temperature lines with a lot of substances, there is a point where theoretically that substance can exist in 3 different states simultaneously. And in physics, they call that the triple point. And it's kind of cool. So, water has a triple point where at a specific pressure and a specific temperature, it will exist as a gas, a solid, and a liquid simultaneously. Interesting stuff. Quick comment from Jim, and then we'll go down to Bob.
Yeah, okay. Interesting sideline. Water, seeing as it's the average, that means there's molecules that are going faster than the temperature and molecules that are going slower than temperature. So you take a glass of water, and there are some molecules there in the glass of water that are small enough to be ice, and there are some that are fast enough to be steam. And so basically, like when you sweat, what's happening is the molecules that are going fast enough to be steam escape. And once they escape, they're going for the mixture, so the average energy level now goes down. And that's why you feel cooler when you sweat.
It's a good point. And there is such a thing as evaporative cooling on an industrial scale. In drier climates, you can cool off a room or a house using evaporation. Doesn't work as well up here, but on a dry day, it does work. And there's still cooling systems in industrial size cooling systems that can do it, even with some humidity in the air. But good point. All right, Bob, K2LD, up on the mountain where it's usually colder than here, but not always. What do you have for us tonight?
Well, first off, it's snowing up here. I don't know if it is down there yet, but it's definitely starting to snow. And I was almost worried that we weren't going to get into the Kelvin scale, but fortunately Jim pulled it out of the hat at the end there because that's just such a lowly misunderstood scale. But lately I've been handling a lot of dry ice because of the way the COVID vaccines get shipped. So have a lot of dry ice to play with sometimes because they send it with like 40 pounds of dry ice shipper, and it's mostly all there when we get it. So sometimes I get to look like a mad scientist and put it in water and let everything bubble out and leave it up on the counter and play with that for a little bit. Let's see. Drop. Coldest temperature I was ever exposed to body-wise is 40 below zero. One of my trips to Alaska, they had a Alaska experience room where they had this room set at 40 below, and they let you go into it for up to a minute at a time. And it didn't really seem all that cold when you first got in there, but after about 10 or 15 seconds, boy, did you want to run out of there quick. Quite the experience. But sometimes people will do that on purpose. There's a medical place down in Catskill, or I should say up in Catskill compared to you guys, that does cryotherapy, where they bathe you in fumes of liquid nitrogen for a set amount of time to chill your body down and make your pain go away in different spots. So just I'll throw it back to that.
Interesting. Well, at some point, your pain would definitely go away, and as would everything else. But that is cool. Sorry, that wasn't intentional. Yeah, I just brought up on my one of my cameras outside while you were talking, Bob, and yes, it is snowing here as well. We're still forecast for, I think, 2 to 4 inches here before it changes over. So, extreme cold, and there's certain things that they use things like liquid nitrogen for in just everyday industry, everyday business. You're seeing it more in cooking. There's things that they can do and create some really interesting things by using that. And in medicine, one of the things that you can even buy a home kit for now is using extreme cold to freeze something like a wart and remove it. They've been doing that for years, and there's actually home kits for that now, which might be alarming because not everybody knows how to do everything correctly, but certainly interesting. I know I really couldn't tell you what the coldest temperature I've ever been exposed to was. Probably if you look back through the records of cold temperatures in this area. I grew up here, and I seem to remember when I was a kid that we had some nights where it went down, 20 below zero or lower. I could be wrong, but I think it's happened. Well, that's probably the coldest I've ever been exposed to. Or it could have been when I used to do my sales runs up to Watertown. It gets pretty cold up there. So anyway, we're getting our usual flow of spam comments. All right, Jim, any comments on Bob's round?
Yeah, yeah, that'd be cool to have some dry ice to play around with. Lots of things you can do with it. And yep, I looked out. It is snowing here as well. So I'm on the HT now. Let me get back onto the other rig. KWBHM.
All right, Jim. And yeah, I wanted to comment on the dry ice as well. Growing up in the dental business, as my family owned a dental supply company, a lot of the products that were shipped to us were supposed to be kept cool. Usually the plastic resin restoratives and a couple other things. And in the summer, they were shipped in dry ice. And every now and then, some of it would still be intact when we got it. And a great example of sublimation, because dry ice, as it melts, turns to a gas. And there is a pressure where water will do that, where ice will turn directly to vapor. And that's how they do freeze drying. You freeze something solid, put it in a vacuum, and you can remove all of the moisture from it without getting it wet. It's a pretty neat idea. And one of my first exposures to that was as a kid. They told us one time about a library that had been the victim of, it was either a small fire or a false alarm, but where the sprinkler system had gone off in the library and soaked all of the books. And they were about to just put them into a huge dumpster. And one of the science teachers in the school had rushed into the school and said, no, I'll collect them. And they sent them off to an industrial, cold storage place and froze all of the books solid until they could find some place that could put them into a vacuum chamber and freeze dry the books. And most of them were still okay after they did that. Just interesting stuff. And that's when instant coffee used to be a big thing. And some of the brands are freeze dried. And basically what they're doing is they're brewing coffee, freezing it solid, putting it into a vacuum, and then what you get is this brick of almost feels like that foam that they use for artificial flower arrangements. And then you just kind of hit that with a hammer, and you get these little crumbles of instant coffee. So cool stuff. All right, next up on the list, hopefully, Matt, you've hooked up to a better antenna, but KB2 GGF from Carhunxon. Your turn, Matt.
Thanks. Pardon me. Thank you, Neil. Little frog in my throat. Yeah, sorry about my transmission before. I was in the kitchen on the HT, and I didn't want to miss the net. So, but I'm on the big rig now. So, yeah, cold, and different states of matter. I've heard glass referred to as a supercooled liquid. Well, what is mercury classified as then, I wonder? And heat loss. Where does it go? Is it absorbed merely by the air, or is it absorbed by water molecules in the air? Is it dissipated some other way? It's an awful lot to think about with cold and heat. And I'm enjoying this conversation and learning a lot, so I'm going to step aside and let other people contribute because I'm about done. KB2 GGF. Back to net.
W2NDG on the OMARC Sunday night Science and Technology Net. Thanks, Matt. And yeah, your signal was perfect that time. Glass as a supercooled liquid. That is a really interesting topic that I don't know a ton about. But I know that is what glass is. Glass is a supercooled liquid. And it's one of those things about physics and matter where an object is not, it doesn't fit into the A, B, C, and D slots. It's, one of those things that's both or neither. And I know the funny thing about glass, because it is technically still a liquid, is that it's still flowing. And the example of that someone once showed me is in a really old house that still has its original glass panes, the old style glass panes in the windows, is that if measured, the glass will be thicker at the bottom of the pane than it is at the top. Someone showed me this once when they were redoing an old house. Really cool. But yeah, the glass flows very slowly, but it's still flowing. Mercury. I know Jim will probably correct me or expand on whatever, but as far as I know, mercury is simply a metal that has its state at room temperature is that of a liquid. And it's interesting because, it has a lot of the properties of some metals. It conducts electricity, and but it's stable as a liquid at room temperature. I would imagine there's a temperature it freezes at, but it's probably very, very low. And I'm also aware that mercury can exist as a gas because we're used to have, I don't know if they still exist, things called mercury vapor lamps that deal with mercury in that state. So, all right, let me throw it over to Jim for comment.
Yeah, okay. K2BHM here. Yeah, mercury is a liquid metal. It does have a freezing point and a melting point. Your fluorescent light bulbs, they put a drop of mercury inside. And in operation, it turns into mercury vapor, and it generates ultraviolet light. And very white and high frequency bands. And it's the phosphor on the inside of the tube that's excited by the ultraviolet rays and generates visible light rays. It's kind of like a transformation. So, interesting property there. And, what else? Interesting about conductivity. How efficient does something transfer the heat? Let's say you've got a car hitting a car. If one car is doing 60 miles an hour and the other's doing 30, the one that's doing 30 is going to get sped up, and the one that's doing 60 is going to slow down. So it's the same type of thing there. But the difference is you have a solid steel bumper, like the old days cars, or do you have a foam bumper like the new ones? That's going to be into the properties. And let me drop a second. So where are we going with that? Well, let's say you got a transistor and it's generating heat, and you put it on a heat sink, and you expect it to take all the heat from the transistor and dissipate it. Well, if you just go and slap the transistor up against the heat sink and put a screw through it, that interface between the two metals has air between it, and it's got a very poor thermal conductivity. But if you put this special silicone grease on it, now all of a sudden it's a lot more efficient in conducting the heat away from the transistor to the heat sink and therefore to the outside world. So good example of thermal conductivity. Back to you, K2BHM.
Thanks, Jim. I'm so glad you're here with us for topics like this. I know a little bit about a lot of things, and Jim seems to know a lot about a lot of things. All right. Next up is Lou, KD2TVS. Lou, anything you want to add to tonight's cold discussion?
Good evening, Neil, and everybody else on tonight. KD2TVS here. Cool, yeah. I think probably the safest thing I can say probably is that when it's a hot summer day, I'm glad for air conditioning. I grew up as a kid in New York City, and we didn't have air conditioning as kids until we became a teenager and we moved into a high-rise. And that was my first experience with being able to put on an air conditioner and staying cool in my bedroom and sleeping well instead of like crazy hot nights in the city. But let's see, my only experience work-wise with cooling systems would be on airplanes, and they were basically the old 707s used to have what they used to call freon packs, and it was just basically like a big air conditioner in the belly. And as the newer airplanes emerged, they went into something called air cycle machines. And if you want an explanation of that, you can Google it, and there's a good explanation on Wikipedia from what I see. It's pretty detailed. It's pretty good, I would imagine. They evolved over the years, and I remember another experience. I actually going down to New Orleans and actually experiencing those swamp coolers down on Bourbon Street, and how well those things were cool that they could actually leave the front doors of most of these restaurants and music places open, and there was like a blast of cold air coming out of there, and it was wouldn't lose it to the I guess to the outside air. It wouldn't exchange. They would stay always cool in there. So basically, that's all I have about air conditioning. And other than it's nice, it's in the 20s now down here now. After getting up this morning, going out around 7:30, I think it was, and it was -2. So let's hope that warm weather comes tomorrow, and all this cold weather turns into a little rain and melts most of this stuff away, or not all of it. So back to you, Neil, and everybody else, KD2TVS.
Thanks, Lou. And yeah, different air conditioning technologies, refrigerant, obviously the most common one that we use, evaporative. And the thing about refrigeration technologies, as we see now, is that, a a lot of these things can be reversed because you're not, once again, like we said, we're not pumping cold air into something. We're removing heat. And all of those processes can be reversed, which is how we get heat pumps. There's a solid state version of all of this where it gets really neat. And there's something called a thermocouple. It's been around for a while. And the whole idea of a thermocouple is that it's a bimetallic device. And if you get the two metallic parts of this at a different temperature, you create a temperature differential. So one part of this device, the one metal, is extremely cold, and you take the other metal and make it extremely hot. The difference in temperature between those two joined metals will create an electric current. I have a little fan on top of my wood stove that works like this. It uses the heat of the surface of the wood stove and the differential between that and the general temperature of the air above it, because it has a large fan-shaped heat sink on the top of it. And the difference in temperature between the bottom and the top of this device produce enough electricity to get a fan spinning. It's kind of cool. But you can take that thermocouple technology and you can reverse it like you can with so many other things like this, like a motor and a generator. So if you apply voltage to a similar device, one part of it will get hot and the other part will get cold, or a solid state heat pump, removing heat from one side and transferring it to the other. And let me drop. W2NDG on the OMARC Sunday Night Science and Technology Net. It's referred to as a Peltier cooling device. And they exist in a number of household objects. For one, these little thermoelectric picnic coolers or mobile coolers. They make larger, more industrial ones. I have one. I have a Coleman thermoelectric cooler that's the size of like a small dorm fridge. And it works. I've used it successfully, camping and in other places. They're not as efficient as refrigerant cooling. They can only create up to a certain differential in temperature. But the reason why I know that you can reverse these and they work in different ways is there's two things that you can do with these depending on how they're set up. One is that most of them allow you to reverse the polarity. And usually there's a connector on it with usually blue and red, indicators, and you can flip it around and line up the red with the red or the blue with the blue. If the blue is lined up with the blue, the cooler is a cooler. And if you flip the polarity around, it becomes a warmer. It won't bake anything, but it'll keep something warm. But the other funny thing is if there isn't any backflow protection, which I would imagine is usually done with diodes, you can actually see the things generate voltage if you put them into a certain situation. I had this happen where I didn't have the electricity to run the thing, but I had some ice or ice packs. And so I put ice in the large Coleman cooler that I have and put stuff in it, closed the lid, but it was in a very hot place. And it generated enough electricity to run its circulation fan. The fan started running. And at first it kind of threw me off. I was like, how is that happening? And then I thought about it. It's generating its own electricity because of the temperature differential. A lot of those coolers won't do that because, like they said they have protection against the electricity flowing the other way into the fan. But this one, I guess, does not. So interesting stuff. Comments from Jim, and then we'll see if there's anybody else out there.
Yeah, thanks, Neil, K2BHM. Yeah, those Peltier effect modules are fun things. Basically what's going on is you have two dissimilar metals, like chromel and alumel, or platinum rhodium, or iron constantine, and you take those two different types of wires and you connect one end together and beads it up. And the other end, you get a voltage generated depending on the difference in temperature between the bead and the rest of the length of wire. So now if you take a bunch of thermocouples and put them in series, and you take the first one and put it on the hot side, and the second one put it on the cold side, and the third one put it on the hot side, alternating back and forth like that, they will actually summate. So like the thermocouple that you use for your gas pilot light, that is hundreds of thermocouples alternately stacked like that. So the one side, all the odd number ones are in the heat, and all the even side ones are out of the heat. And it generates enough electricity to keep the gas valve on. And then Peltier came along and found out that if you put electricity into it, instead of taking it out of it, you can create the hot on one side, the cold on the other side, and there comes the Peltier Effect module. And like Neil said, I've got a Coleman cooler for the car, plug it into 12 volts, and one side gets hot and the other side gets cold, and you can reverse the plug and make it heat or cool. So very cool. We used Peltier Effect modules on the optical tweezers so that we could modify the temperature of the sample when we were measuring forces of attraction when we were unzipping DNA. So they can be very handy. Back to you, K2BHM.
Oh, yeah. Cool stuff. I don't deal with it too much at work, but I know there's some systems there that do have active cooling using that technology. Some of the higher end compute clusters, which I don't deal with directly in my department, but trying to get things to cool without them sounding like jet engines, it is a way to supplement the cooling. And you can definitely build computers at home and buy computers for extreme gaming and other high-end computational things that have that type of cooling in them. So neat stuff. Thanks, Jim. Thanks, everybody, so far. And you are listening to the Overlook Mountain Amateur Radio Club's Sunday Night Science and Technology Net, hosted by myself, Neil, W2NDG, and Jim, K2BHM. And we'll see if there's anybody else out there who would like to participate in tonight's discussion, which is the main topic is cold and what cold is, and if you have any stories about it, practical uses for it, or the scientific side of it, which Jim and I have been tossing back and forth. So please come now with your call sign, your name, and your location.
And for you, I do want to comment.
All right, Paul, go ahead.
I remember 1981, I was in the Navy, and I got to a place called Brunswick, Maine, and it got really wicked cold, as they call it. I went and dug up the weather history at the Naval Air Station and found it. They got that 28 below on January 4th. And I can remember sometime around the New Year, the pipes froze in the Paris, and it was so cold in there, it was like, holy cow. Then about 10 days later, we ended up going to Iceland. And the temperature never dropped below maybe 10 degrees the whole time I was there. Hence for you, IQ.
I know one of the more strange phenomenons in extremely cold climate is ice crystals. And it's something I've never experienced in person. I'm going to actually throw that one over to Jim real quick. But I remember, and it's something I mentioned this morning on this morning's net when we were talking about the weather, and I mentioned that the old Ray Falconer weather forecast on WAMC, when he would mention, the current conditions in Mould Bay, Northwest Territory, and other crazy places where there's extreme weather. But sometimes when he would mention the conditions in one of these places, either Messina, New York, or different places up in the Yukon and Northwest Territories, the description would end with the phrase "with ice crystals," and I believe that is some sort of airborne phenomena. I don't know if you know anything about that, Jim.
Would you be referring to rime ice?
I'm not sure.
Yeah, we were dealing with that when we were setting up the scientific equipment to do the environmental measurements on the ocean-going research vessel that was going down to Antarctica. When things get that cold, the moisture in the air will actually contact surfaces, metal, trees, whatever, and generate an ice coating on the surface just from the fact that it is freezing moisture right out of the air. And we had to come up with heaters to heat up the instrumentation and the tubing and stuff like that, because down Antarctica way, if we didn't, it'd be nothing to build a foot-thick layer of ice on everything down there on the external areas of the ship. So, yes, moisture in the air is freezable.
W2NDG on the OMARC Sunday Night Science and Technology Net. And I do seem to remember that when that phenomenon occurs and it's sunny out, that it's spectacular and possibly even blinding.
You're not talking about sundogs.
I'm not sure.
Well, you get ice crystals in the upper atmosphere, and it causes sundogs, and like a ring around the sun, and along the horizon, it maybe like a little bulge in the ring. Kind of interesting. I saw one in Middletown a couple years ago.
Yeah, I just looked this up. Halos, sundogs, and light pillars. Jim, do you know anything about this stuff?
Just the old farmer's tale about the ring around the moon indicating that some weather is coming.
Yeah, cool stuff. But yeah. Halos, sundogs, and light pillars. And a lot of that's caused by those ice crystals in the air. Cool stuff. All right. We had Paul's comment. Is there anybody else who wanted to check in before we bring it back up to the top? Oh, and that's Alec, KD2YFU from Hudson. Alec, you're a little weak, but you're readable. I know this is a topic heading into an area that you're quite well versed in as well. So, do you have any comments on the discussion so far tonight? Alec, if you're still there, probably that all that weather between you and the repeater is not helping things. We have to get you set up with something with some more watts and an antenna sometime. But some of you may know Alec is my son, and a recent ham radio license recipient. With everything going on and the pandemic and everything else, we haven't had a chance to really set him up yet. So hopefully we'll do that soon. Let me see if he's still there. We'll have him try again. Nope. That's why I just texted him that. So, Alec, we'll get you set up. Alec is not using the red radio, as the OMARC people call it. He is using an older black radio, a UV5R, that I gave him when he was learning so he could listen in on things. But I have to get him set up with something better because he's just using standard UV5R with the stock antenna up there. So, all right. Alec, you can type any comments you wanted to make into the YouTube chat, or you can just text them to me as well. But I'm going to move back up to the top, and I will interrupt and throw whatever you wanted to talk about in there. So up to the top would be Paul, N3EYQ, who just commented on sundogs.
Atmospheric phenomenon of light refraction through the ice crystals in the sky. I've always seen it like just before, storms and stuff like that, where you get the high ice and stuff like that. Interesting, fascinating. Getting back to that, it's like I 28 below zero. Actually, I don't know why they say minus 27.9, but I don't know. Who had that kind of accuracy in meteorology back then? Maybe the Navy did. It was at a Naval Air Station in Brunswick, Maine. That whole week, those 3 or 4 days, it was below zero at night, and I think I don't remember. I have to look at it again. Portland, Maine historical. Let's see here. I might have it here. No, I changed it to a different county. But I think it might have broke 5 degrees during the whole day that day. Yeah, wicked cold, they say. You know what wicked cold is to Maine. And for you, I feel.
Oh, yeah. And let's see. I was just poking around for some records here. I thought maybe one of these had happened during my lifetime. Poughkeepsie, New York. Lowest temperature ever recorded in Poughkeepsie, New York was minus 30 degrees. That was in January of 1961. The highest temperature ever recorded in Poughkeepsie, New York was 104 degrees on August 1st, 1933. So, interesting stuff. Coldest year on record was 1958. Warmest year on record is a tie between 2012 and 1941. So that's for Poughkeepsie, New York. So I know I haven't experienced colder than that. But I have to think it got to 20 below once in my lifetime. Next up is Bob, K2LD, up on the mountain.
Yep, still snowing up here. The coldest I remember it being ever up here was 14 below. Not wind chill, that's actual air temperature. But it's really about it for me. My mind is just not thinking correctly because I have to get to sleep soon because I have to get up early to plow before I leave for work because I'm supposed to get 14 up here. So I gotta make sure I get up shut eye. So I'm gonna be taking off at this point. Enjoy the net and farewell to all. 73 is K2LD.
All right, thanks, Bob, and good night. And maybe we'll hear you in the morning. be safe and keep warm. And yeah, I'm kind of glad we're not getting that much, but I feel bad for you. So have fun managing your frozen water in a crystalline format. All right, Matt, KB2GGF, we're up to you.
There it is. I thought it'd never drop. KB2 GGF here. Yeah, cold. I never used to get cold when I was young. But like after age 55, 57, I noticed that my hands started getting cold. And that never happened to me before. And now I don't like cold much, but I think a lot of it is really just acclimatation. If you spend a lot of time outside, you get used to it, and if you don't, you lose it. So, yeah, but cold's not so bad because you can warm up. It's a lot harder to stay cool. Can't think of much else. So back to that KB2 GGF.
W2NDG on the OMARC Sunday Night Science and Technology Net. Thanks, Matt. And yeah, another thing that it gets discussed frequently is that humans are a lot more adaptable sometimes than we give ourselves credit for. And oh yeah, the way you can see that, I remember my brothers telling me, when I was a little kid, they flew to Texas to spend a week with their great aunt Ruth in San Antonio, and her daughter and their kids, who are my cousins, and they were telling me that it was the fall or winter here. They got into like the high 60s there, and they went into these caverns one night, and took a tour of these caverns. But whatever it was, on the river tour through San Antonio or in the caverns, all the people down there were freezing. They were wearing winter coats, and it was maybe 68 degrees, and it was too cold for them. And the whole time, my brothers just kept getting asked, "Aren't you freezing? Aren't you cold?" And they're wearing like t-shirts, and they had come from cold weather into that. 68 degrees felt warm, but to the locals, it was freezing. And that's what happens. We get used to it. We go through one of these heat waves, and as long as it's not ridiculously humid, I can get used to heat. I've lived in places without air conditioning, and you deal. If you have to deal with it, you deal with it. If you absolutely can't take it anymore, you go to a mall or something and walk around for a few hours and cool off. But I certainly did it enough times. I think as we get older, we get less tolerant of it. I certainly don't think I could deal with it anymore, but I do have, I am able to deal with heat better than I was maybe 10 years ago. And that's just being in better physical shape, I think, is part of that. Let me drop. So Alec, KB2YFU, did type what he wanted to say on the radio, apologizing that the little Baofeng's not making it tonight. But he was going to say that the old wives' tale about the ring around the moon isn't too far off. Mid-latitude storms are often powerful enough to throw moisture high into the troposphere, causing rings like that. So sometimes it's actually a good indicator of incoming weather. Thanks, Alec. Interesting stuff. Alec was a meteorology major for a couple of years before he decided to become a computer programmer. So he does have a pretty good meteorologic background because it was always an interest and a hobby of his. Anyway, at some point we'll have to get him involved in the weather nets, right? And that leaves us with Lou, KD2 TVS. Lou, we're up to you.
Okay, Neil. Yeah, past comment, you guys were talking about thermocouples. That was interesting because I tended to deal with those. We used to use those on engines to you to go to the indicator, so you'd get your, I guess it would just analog signal, whatever, just right to there, and get your exhaust gas temperature. And yeah, you were also talking about those little fans that you used on the fire stoves and stuff like that, wood stoves, and how they spin around. I was just yeah, I've been looking at a couple of those. I think they're probably going to be replacing changing a fireplace insert into a wood stove at the house, and they're thinking of getting a couple of those, I guess, to put up on top. I've seen a couple of people utilizing them. And what was on your other comment on that little Coleman cooler? Yeah, I've seen those. They're pretty interesting, but I completely forgot that you could actually swap them to keep something warm or to really cool stuff off. Drop a second. Yeah, they were thinking about the coldest I was ever out in. I remember it was on a ramp at JFK. Well, it was wind chill factor more than anything else, but I remember 40 below, and that hurts when you're out there. You talk about getting used to, temperature extremes. And we talk about, my son's out west in Nevada, so he apparently likes that heat. I don't mind it, but I don't want to be out there in the blazing heat of the desert. You need some shade. I always find shade is helpful, but it can get hot out there. I remember years ago working with a guy that I knew would always work inside the hangar. He was never exposed to having to work outside the hangar. And one night he was outside with me, and I was basically used to working the line all the time with winter gear in the winter like that. And he couldn't function out there. I actually had to send him, listen, go up on the airplane and warm and thaw out, because I hate to see you shivering in front of me. And I just, when you're out, you work the line outside, you just want to, just rush through it and get it done. And basically, you just want to get back inside into the warm, or you take a break every once in a while. But yeah, you got to bring it back memories. So that stuff. Back to you, Neil. KD2 TVS.
Thanks, Lou. And I can think of two references to thermocouples from when I was a kid. One of them was a project in a magazine that my brother had, or possibly a book. It's my late brother, Paul, had shown me this because it had to do with radio. And he knew that I was interested in anything like that, dealing with radio. And it was a very simple one transistor radio that had been designed for the third world. And it used a single transistor amplifier, basically a crystal radio design. And it wasn't designed to be tunable. The way it was set up to have a very open front end, and it would simply pick up the strongest station around, which usually there was only one station in a lot of these communities. But it could be adapted to a mild tuning circuit, or built to be a little more narrow band. But a single transistor amplifier, and it was powered by a thermocouple. And there was an open space on the bottom of it, and you would put it over a candle or a small bit of tinder or something, and it had like a metal chamber on the bottom that collected the heat. And then the thermocouple used the top part of the radio as the differential, the air above it. And that's what gave you the power for amplifying whatever you're listening to. It didn't drive a speaker, but it drove an earphone. And it was a power-free radio that outperformed a crystal radio. They gave these away in a lot of communities, but they released the project so people could make them for other people. That was one. The other has to do with the James Bond movie, The Man with the Golden Gun, because that's what the power generation was on that island at the end of the movie, when they put the mystery device that was stolen They called it a super efficient solar cell, but that's not really what it was. In reality, they were using the temperature differential between the solar collectors and the vats of, I think it was liquid nitrogen, could have been liquid something else, but I know that the henchman falls into the liquid and gets frozen, and that's typical bond ending, and then the place blows up when the temperature gets too high. So, but yeah, another thermocouple oriented thing. There was a company maybe about 8 or 9 years ago. W2NDG on the OMARC Sunday night, Science and Technology Net. There was a company a while back that was selling a cooking pot. And they were selling it for camping, but you could technically do this at home as well. But it would take the differential between the bottom of the pot and what was in the pot. So the metal on the bottom versus the metal on the top. And the pot had a USB jack on the end of its handle, and you could charge your phone with it. Just boiling water, eventually, the power level would go down as the water got hotter. But what they said was, when you're camping, you could throw this thing on or near your fire and keep filling it up with snow if you were camping in the winter, or just ice if you had any ice. And after a couple of fills with ice or snow, you'd have enough power to get your phone charged up enough to make a call in an emergency or charge it for an overnight. An interesting idea. It didn't stay in their line very long. I have a feeling it didn't perform as well as they wanted it to, but it was still cool. I don't have one, but I thought it'd be neat to own one. All right, let me drop. Is there anybody who would like to check in at the end of the OMARC Science and Technology Net here? Please come now.
This is WA2 RKN. Jerry. Hi, Mark.
Jerry, welcome to the net tonight. I don't know how much you've been listening, but we've been talking about cold. That was the main subject, but explaining the physics of it, that cold is not really a measurable force, but it is the absence of another one, which is heat. And then we've been talking about various things, weather phenomenon and Peltier coolers and all sorts of things. Sublimation. Jim gave some really good physical background on it. So, do you have anything for us on the subject tonight?
Yeah, I've been listening basically the whole net. I didn't check in earlier because I didn't really think I had much to contribute here. I still feel the same way. Yeah, I understand the topics, the discussion that was going on. I used to be a physics major. So just basically checking in to let you know that, there's somebody else out here just listening and really nothing to contribute. WA2RKN back then.
That's okay, Jerry. And frequently, I love when you get into the discussions with us because you always have some interesting stuff to throw at it, usually. But we'll catch you another night, I'm sure. All right. Anybody else before we close things up here?
This is KD2KJU, and I'm pretty much in the same boat with Jerry. Definitely really enjoyed the conversation tonight. Just didn't have much to contribute, but I really enjoyed everything I was hearing. Great net. KD2KJU.
Thanks, Jed. All right, and some final comments from Jim. Jim, it's a shame like thermocouples aren't more efficient, right? We could have a hot water powered snowblower.
Yeah, that'd be cool. KTBHM. Just a couple final thoughts. We're talking about thermocouples, and their original intent was to measure temperature, and then we found other things you could do with them. But getting back to measuring temperature, yeah, we're used to the mercury thermometer, where the height of the column of mercury changes depending on the temperature because of the what's called the coefficient of linear expansion. Things grow or shrink with changes in temperature, and that is different for all materials. And like some thermometers have the mercury in them, which is a no-no now. So they have a red-colored alcohol liquid in, which also expands and contracts quite a bit with temperature changes. And then we got the thermocouple, which does electrically. But let me go off on the sideline a minute. Let me drop. Let's say you've got two pieces of metal. I don't know. Let's, for the sake of argument, say they're 1/4 inch wide and 6 inches long, and maybe about the thickness of a piece of thin cardboard. And you put the two together back to back, and you take the ends and weld or solder or glue or something, but firmly attach the two ends, each end of the two metals. And these metals are different materials, so they're going to have different coefficients of expansion. So at that particular temperature where you glue it, the thing is going to be straight. And as the temperature goes up or down, one side is going to grow and the other side is going to shrink. And that's going to cause it to bend. They call it a bimetallic strip. And you can actually put an electrical contact at the end of that bimetallic strip and let it make and break a circuit, depending on the temperature. And with that, you can make a thermostat or an old-fashioned car flasher for the signal lights. And one more site, let me drop. So that is very similar to what's going on, the electrical equivalent of the mechanical situation with the thermocouple. Maybe that clears things up a little bit. But we do have another way to measure temperature. When you check a diode, you put it on your multimeter. You put it one way and it reads blanked out because it's over 2 volts. You put it the other way and it reads like 430, 450, 470, something like that. Well, to test the diode, they're putting a certain voltage across the junction and trying to maintain a current of whatever. And that's how they measure the resistance. Well, in the case of the diode being one way, it's open, so the voltage soars up above the 2 volt scale, so it's probably like 3 or 4 volts or whatever, and the scale blanks out. But the other way, the diode is conducting, and you're seeing the forward voltage junction drop, which is about 430, 450 millivolts, 470 millivolts, whatever, depending on the material. But it also depends on the temperature. You can very closely monitor that temperature and calibrate it and use a diode or the base junction of a transistor and some electronics, simple electronics, to measure temperature. So, more than one way to skin a cat. Back to you, Neil. Enjoyed it tonight, K2BHM.
Thanks, Jim. And yeah, that bimetallic thing you see when you open up the thermostat, it's that spiral. And then you're getting back into mercury again because, yeah, that was the most common way of using that bimetallic strip to turn the thermostat on and off to get that open or closed connection was a little bulb filled with mercury that would lean one way or the other. And they don't do that anymore. But definitely, a low-tech way to do something that worked, and in much higher tech ways, of course. But we still measure temperature mechanically. And I'll tell a little funny thing here real quick before we close up. Those of you who are fans of the Discovery Channel's How It's Made, there is an episode where they show a company making precision glass thermometers. they are, they go through the whole process of them drawing them out, blowing them in, so that they have the hollow space in the middle, and measuring how much they hold, putting the correct graduation marks on them, filling them with the red dyed alcohol, calibrating them, the whole process. And as you're going through watching that, the gentleman, and you never see his face, I think you see his back and his arms and his shoulders through the entire thing, is my brother-in-law. That's what he does for a living. He works for a Precision Instrument Company, as did his father before him, my father-in-law. So we still do measure things mechanically. A lot of these companies have gotten into very high-tech ways of doing it, but sometimes the old methods can be the most reliable. Anyway, let's close things up. Do we have any last-minute comments? All right, nothing heard. I'd like to thank everybody for checking in tonight, and thank my co-host, Jim, K2BHM. And let's close things up. You have been listening to or participating in the Overlook Mountain Amateur Radio Club's Sunday Night Science and Technology Net. We meet here every Sunday night at 8 p.m. on 146.805, the repeater sponsored by the Overlook Mountain Amateur Radio Club, with a negative shift of 600 kilohertz and a PL tone of 103.5 hertz. We ask you to join us here on this repeater for the other nets that occur on 146.805. Every morning at 8:35 a.m., we have the 8:35 on the 805 net. That is a casual roundtable net hosted by a rotating cast of OMARC characters. The net was originated by Paul, AC2UQ, and Bob, K2LD, at the beginning of the pandemic to keep us social, keep us in touch, and make sure everybody was okay. And the net remains to this day. Also, every evening, every day, in the evening at 6:30 p.m., we have the 6:30 p.m. check-in net, a similar net to the 8:35 net, but held in a directed fashion by net control, and once again hosted by a rotating cast of OMARCians. Every Monday night at 8 p.m. is Undernet, UNDR, or Ulster Northern Duchess Readiness Net, a net getting our members and other ham radio operators of the area ready to be able to react in the event of an emergency, and possibly in the future affiliate ourselves with one of the several emergency agencies that operate either in amateur radio or close to it. Right now, we're just demonstrating and teaching, and there's some interesting technology in that net as well. Come by and check it out. Monday nights at 8 p.m. Every Wednesday at 4:30 p.m. is our first HF net, and that's Paul, AC2UQ, and some other hosts, but Paul is the founder of the net, hosting the Hudson Valley 80-meter net, and that's for now held at 3835 kilohertz at 4:30 p.m. on Wednesdays. Every Thursday evening at 8 p.m., our president, Dave K2JLV, hosts the Thursday Night Technical Net, a net similar to this one, but usually more of a ham radio topic or ham radio related topic. And Dave will take check-ins and look for somebody who has a specific thing they want to ask about or a problem they're trying to troubleshoot. And if a topic doesn't gel in the first round, Dave spins the topic wheel and comes up with one for us. Definitely a fun net, can run 4 or 5 rounds late into the night. Please stop by and share your techspertise. And now we're closing the Overlook Mountain Sunday Night Science and Technology Net, and returning the repeater to regular use. If you would like to know more about our club, would like to become a member, please stop by our webpage at omarcclub.org, omarcclub.org, and check us out. This is Neil, W2NDG, closing the OMARC Sunday Night Science and Technology Net. 7-3 to all. Have a good night. Be safe in the weather. And as usual, I'll hang out for a few minutes if anybody wants to chat. Good night.